Hi, thanks so much for having me. My name is Jessie. I'm here to talk about the Split-Trust Encryption Tool. Also known as STET, this is a tool for encrypting and decrypting data, and the goal is to provide a way to securely send data in and out of cloud with guarantees that the only entities that can access this data are the originator and the consumer. So I'm going to start by going through a general example of a workflow with STET. So we have on the left here an on-premises machine. This is the data originator. And we trust this because it's completely within our control. And on the other side, we have a confidential VM that is the consumer. And this is the part we want to send data to. And we trust that because it's running with confidential computing. We also have a storage bucket that will store the encrypted data in the interim. So the on-premises machine is going to upload data to it and the CVM will download from it. And this is not required when using STET. STET is really just an encryption decryption tool. So once the on-premises machine has the data, you can do what you want with it. You can put it in storage, you can send it to the VM directly, but it's here to, the bucket is here to show that your encrypted data can sit somewhere outside your trusted machines and still be protected. And lastly, we have the key management system that stores the key encryption keys, the KEKs, that will be used by STET. In this situation, there's only one KMS, so you have to trust it here. If a malicious party within the KMS got access to your encrypted data, they would have everything they need to decrypt it. But we'll talk later about how STET addresses this. So visually, this is what workflow for STET looks like. So the on-prem machine is going to execute STET encrypt. It provides the data you want to encrypt and a config file as input. The config file just contains information like the URIs for your KEKs and the type of data encryption key or DEK to generate. So the data is encrypted, the DEK is encrypted by the KEK, and then the ciphertext and encrypted DEK are outputted. This all gets uploaded to storage, then downloaded by the CVM. And the CVM's workflow is essentially the reverse. We execute STET decrypt, decrypt the DEK, decrypt the data, and you get the plain text as output. So STET aims to improve on this previous workflow in a couple ways. The first is to reduce the amount of trust that is needed. I mentioned in the previous example, you do have to trust the KMS there because there's only one. But STET has a split trust feature, which allows you to use multiple KMSs together to avoid unilaterally trusting either one of them. And the second way it tries to improve the workflow is that in cases where trust is needed, we make sure to fully establish it using attestations. So your KEKs can be configured to only allow access based on attestation information. This can be platform-based, so only releasing the key to machines that can show they're running with confidential computing. Or if you're using confidential space, these attestations can be workload-based. And I'll go over each of these features in a little more detail. So split trust first, and to reiterate, the purpose here is to avoid the need to trust a single KMS, and we achieve this using secret sharing. So during encryption, you can configure it so that the DEK is split into multiple shares, N, each of which is encrypted by a different KMS. So for example, you can have N equals 2, one encrypted by Google's Cloud KMS and one by an EKM. You also will specify a threshold K, and this represents the number of shares that are needed to reconstruct the DEK, and this can be less than or equal to N. A really important feature here is that having less than K shares reveals no additional information about the secret. So in the previous example I mentioned, if we have N equals 2 and K equals 2, even though each KMS has one of the two shares needed to reconstruct your key, having one share is computationally equivalent to having 0. They don't have any additional information from it. So maliciously accessing your data would require collusion between these two KMSs. And during decryption, we do the reverse. So each share gets decrypted by its respective KMS. And if there are enough shares available, then we can recombine the DEK to decrypt your data. So visually, this is what it looks like. And the most notable change here is we now have two KMSs. One is in Google Cloud and one is external, an EKM. And now in STET encrypt, after encrypting the data, the DEK is split into two shares, and each one is encrypted by a different KMS, and the encrypted shares get outputted. And on the other side in STET decrypt, each share gets decrypted by their respective KMS before we reconstruct the DEK and decrypt the data. So note that outside of your trusted machines, in this situation, there is no point at which a single entity has the ability to maliciously decrypt and access your data. I'm going to talk about attestations next, and this is handled a little differently for EKMs and Cloud KMS. So I'm going to talk about EKMs first. In this context, EKM just refers to any key managers outside of Google. So we natively support TPM attestations. You can configure your KK to require a TPM attestation in order for it to be released. So when STET communicates with your EKM, the EKM will request an attestation if it sees that the key policy requires it. So if you look at this very simple diagram, it has the same parties as the previous one I was presenting, but the decrypt exchange between the EKM and the CVM includes an attestation. This is not limited to decryption. You can require an attestation for encryption. You can require it for both encryption and decryption if you wanted to, but this is what we consider to be the most common use case. For Cloud KMS, we support attestation with the confidential space attestation token. So confidential space is a separate product we have, and it allows confidential data to be shared in a workload with a TEE without compromising confidentiality or ownership of that data. Part of this is that the workload is issued an attestation token that attests to not just the VM's platform, but also the exact workload that's running. So you can not only require the presence of confidential computing for your key, but also based on whatever the exact workload that's being run by the machine. So the diagram at the bottom here is very similar to the previous slide, but we have a Cloud KMS instead of an EKM. And instead of just a confidential VM, it is a confidential space VM that it's communicating with. So I have a quick recorded demo. I'm going to play this and sort of explain what's going on here. So we start with our keyring in Cloud. And one thing to note is that the Cloud and EKM KKs are both stored in this keyring, but the EKM key is an external key. So it's going to redirect to a key that we've configured in our EKM. And that's this key right here. And we've configured it to require confidential computing for decryption. This is the VM that I'm going to be using in this demo. It has confidential computing enabled. We're going to do that. And this is the storage bucket. So in our on-premises machine, we have our plain text data that we're going to encrypt. And we also have a config file. And this contains information like our KK URIs and the number of shares we're going to split for split trust. So we have two shares the DEK is going to be split into, and we're going to require both of them. Our threshold is 2 to reconstruct the key. So if we run our encryption command, we're providing the config file and our plain text, and we're going to let that run. We're going to take a look at our output. That looks good. And now we're going to upload it to our storage bucket. So once that's uploaded, I'm just going to show really quickly that it is indeed in our bucket, and then we can move on to our VM. So this is the same VM that I showed before, running with confidential computing. First, we're going to download the ciphertext from our bucket. And this also has a config file, and it has the same information, the KK URIs and the splitting information. And we're going to run the decrypt command. So as this is running, STET will be establishing communication with both Cloud KMS and the EKM. On the AKM side, because we've required confidential computing for decryption, STET is going to be sending it an attestation. If we were running on a VM that didn't have confidential computing, and this weren't a confidential VM, this is the point at which it would fail because STET couldn't produce the attestation that it's being required. But we are, so it's working. And if we take a look here, we have our original data. So note that in this case, like I mentioned, we're just sending a TPM attestation to the EKM. So the EKM is just checking that we're running with confidential computing before granting access. Again, with confidential space, you could more specifically require a precise workload that's being run, but this is a more complicated use case to walk through. So you don't really have time to go over that in detail. So anyway, to summarize, STET provides a secure way of sending data in and out of GCP that is cryptographically and verifiably protected from cloud insiders. It's a big usability benefit. It manages communications with KMS and key splitting for you. And another note on usability, STET is integrated with GSUtil. So in my demo, I ran this STET and GSUtil commands separately for clarity, but these can actually be combined into one command. If you run GSUtil with the STET flag, it will automatically use STET to encrypt your file uploads and decrypt the downloads. So STET encrypt and GSUtil copy can be combined into one command. The same goes for STET decrypt and GSUtil download. And if you use STET with confidential space, you can use attestations that are workload based, and you also have the confidentiality and ownership guarantees for your data that confidential space provides. And for existing customers of confidential space, STET adds usability and convenience when encrypting and decrypting your data. If you're interested in more info and trying out our quick start guide, we have our repo here. Highly recommend you check that out. And I was only able to go over it very briefly, but for any details on confidential space, my colleague Josh has a talk on it at this conference, and also some documentation that you can look into separately. That's all I have prepared. Thank you everyone for listening.